Monte Carlo simulations. With this, we come to the last topic of the Part A basics of our course syllabus. Let's just review it for a second. We have looked at the basics of probability, random variables, distributions. We have looked at several univariate distributions and then moved on to joint probability distributions, conditional distributions, derived distributions, joint normals, and also convergence of a sequence of random variables. We did borrow one lecture from this week, the third week, to complete the discussion on random variables and joint distributions. So we have two lectures on Monte Carlo simulations. And in these two lectures, I would like to cover the basics of why we resort to simulations and Monte Carlo simulations in particular, how we get random numbers and how to test for randomness, how to generate random samples from various univariate distributions, both discrete and continuous, and then generation of samples of dependent random variables, and then a few words on variance reduction techniques in Monte Carlo simulation. And as we have done all through, we will solve examples and see applications during these lectures. Now, the first question is why simulation? Let's consider a few scenarios. Let's say a new design has been proposed or a new strategy has been proposed, and we would like to know what the performance or the implications of this new design is. What about its safety, its economy, its feasibility? If there are more than one designs, which one would be the best? And instead of building the prototype, we would like to resort to simulation first because of the cost and the time involvement. The next scenario is, let's say, some modifications to an existing system or existing structure has been proposed. We would like to know how well that modification would work, would serve the purpose, but it may be too costly or too risky to fix first and then test. The next situation could be that an existing system, like an existing structure, a bridge structure, needs to be verified for adequacy for continued service. But the test risk is too high, which means the load at which we would know something useful could be so high that there is an appreciable failure probability associated with that stress. So that the test risk could be too high and we would like to do some simulation. The next scenario could be that a real system needs to be learned or mastered, and there are quite a few examples you see. But to learn on the job, it might be too risky, so some sort of simulation would be preferred. The last scenario is that there's a process whose evolution law we know, whose initial conditions we know, and then we'd like to know what happens, how it evolves in the future, what the end point is. So we would need to simulate the process. So the common theme running through all of this is that we know the rules governing the system, but there is no closed form solution which relates the input with the outputs. And in today's world, when we undertake simulation, the computers have a central role. In fact, some simulations are performed entirely in the computer. For our purpose, therefore, it is the process of uh, having creating a mathematical or a physical or a mathematical physical hybrid model of a real system, and then subjecting it to experiments by supplying a set of inputs, and then studying the output or the response of the model. So that is simulation. Now once more, let's have a bouncing animation just to underline the fact that any simulation can only be as good as the model and its assumptions. So one should be careful about putting misplaced faith on the simulation results. Now, simulation of probabilistic events. That's what this lecture is about. So we have seen this description of a concept system. It might have uncertainties in one or more aspects, namely inputs, properties, the capacity, and the model of the system. And if that is so, then we need to, when we simulate the system, we need to incorporate the random aspects of the problem. So we need to be able to simulate random events, and that is what is achieved through Monte Carlo simulations. And Monte Carlo is a famous district in the Principality of Monaco in the south of France, and it's famous for its gambling casino. So that's where the name comes from. Now the outcomes of Monte Carlo simulation is basically it lets us evaluate the expectations of functions of random variables, and in our case this often takes the form of estimation of rare probabilities, like probabilities of failure, or the expectation could be used to establish statistics of a system response, mean, variance, etc., or just the evolution of a random system, which could be random both in space and or time. And obviously this is relevant, very relevant, when closed sum solutions are not available. So Monte Carlo simulations is one of the best ways to tackle such problems.